Welcome to Click for IB Biology. Here we're going to be looking at energy flow diagrams with respect to ecology. This is a way in which ecologists have attempted to turn the descriptive food chains and food webs into quantitative measured diagrams. There's a blank version of this presentation down in the description that you can annotate with your own notes as we go along, but then there's also 10 questions that you can use with answers to test your understanding of the video that we're about to do. There are a variety of ways in which energy systems can be displayed. The left-hand version here is known as a Sankey diagram, and illustrates the way in which the solar energy available here to the autotrophs, much of which turns out to be actually reflected from the surface of the planet and therefore not available to the synthesis of biological molecules. So about 90% of that is reflected. The remaining solar radiation is trapped in photosynthesis, but of that remaining 10%, 8% of the original is actually lost to the environment as thermal energy. Only 1 or 2% may become trapped in the form of biomass, biological molecules. Here we have a system diagram on the right-hand side showing the process of solar energy being available here, and at the first trophic level we have photosynthesis. The diagram illustrates how energy is always continuously lost at each trophic level back to the environment as thermal energy. Energy trapped and fixed by producers becomes available through feeding, herbivory, to the primary consumer. The primary consumer also experiences energy losses in the form of thermal energy and also the death and decay of organisms forming detritus, but as the primary consumer, the herbivore, grows, it becomes available to the next trophic level of carnivores for consumption, and in this way energy passes down through the food chain. Now the matter which has been lost and energy which has been lost to the system through death is then cycled back to the environment through the action of the decomposers, also returning energy to the system but matter back in to be recycled. It's worth remembering here that energy enters Earth as sunlight and leaves as thermal energy. In principle, these two sides of the equation are balanced. The energy which has been absorbed by living systems, by the producers, is used to drive the cycles of matter which we see in the structure of food chains, food webs, ecosystems and biomes of the world. In 1942, Richard Lindeman, working out of the University of Minnesota, constructed the first publication of quantitative food chains, drawing them as what are now famously known as the pyramids. Pyramids can be shown as pyramids of number, pyramids of biomass, or indeed pyramids of energy as shown here. This diagram is constructed from this data here to illustrate how energy passes from one trophic level to the other. Here we have the producers, the primary consumer, the secondary consumer, and the tertiary consumer. And the notable features of this pyramid is that it is a stepped pyramid with energy being lost at each step. If we just look at one aspect of this, then of the producers in this diagram, this energy is transferred through feeding to the primary consumer, but all of this is lost back to the environment, largely in the form of heat. Notionally, students of ecology often speak about a 10% transfer from one trophic level to the next. And whilst this is a useful rule of thumb, within different biological food chains, food webs, ecosystems, and biomes, the actual energy transfers vary a great deal. Notice that this type of pyramid, often seen in text, is incorrect, as there is no smooth transition. It's a stepped process of energy transfer through matter moving from one trophic level to the next by way of feeding. There are consequences to this stepped pyramid structure and the loss of significant amounts of energy at each trophic level. These energy losses mean that the total energy available to the next trophic level is considerably less. The number of organisms that can be supported also decreases, which we have here as well. So these are the two consequences that we initially note. Indeed, Paul Colinvaux, in his 1978 book, famously wrote in one of the chapters why big fierce animals are rare, such as the tiger that we see here, tigers, lions, and so forth, the large predators. Whilst they have very impressive modes of feeding as top predators, we might ask why they are so big. Why are big fierce animals? Well, the reason they're big is that these are evolutionary adaptations to the predator-prey dynamic. Being large puts them in a good position to act powerfully to subdue their prey. The larger size also reduces their metabolic rate so that they can function more efficiently, and their movement over distances is considerably more efficient as well. But the amount of energy which is available to something like this tiger requires large land areas to support just a single tiger or a lion, and this places such animals in a very precarious position at the top of the food chains, where their populations are very susceptible to changes such as disease and a lack of food. These will devastate what are already very small populations. Here's the link to the next video in our ecology course. The channel subscription button, please, if you would. And here's your playlist for the other videos in this particular topic.